Hi, my name is Giragosian, and thank you for giving me this opportunity to submit this video where I can show you my project. To give you a little background about my project, it started when I was a third-year mechanical engineering undergraduate at UC Irvine, and when I was looking for an extracurricular activity that I could be part of. I knew I was interested in space, and I somehow wanted to tie that passion with a project that was going on in school. So I heard about a project where a bunch of students were designing a satellite that they wanted to build and launch into space. I decided to join their team and build a structure for the satellite. Today I'm going to show you that structure that I designed for this team. This is the structure that I want to present to you that I designed. It is the structure of a cube satellite, or a CubeSat. CubeSats are basically miniaturized satellites. The goal of the project was to design, fabricate, and launch a cube satellite. When I joined the structure subsystem, everything was already in its design phase. So it was in the very beginning phase. The first one out of the three. It was in the design phase. It was basically my job to build a structure that could support the weight of everything inside the satellite and survive launch forces. I started by designing primary and secondary structures. The primary structures are the two frames, the left frame and the right frame. And also the primary structures include the 6 panels. The top panel, the right panel, left panel, back panel, bottom panel, and lastly and most important, the front axis panel. The reason why the front axis panel is the most important is because it has the holes that you need for the imager, the antenna, and the serial communication port, where a serial cable connects the satellite to a PC or a desktop so that you can either program or test to debug the satellite flight software. To design the structure of the satellite, I used SolidWorks. SolidWorks is a 3D CAD design package software, and it was very fun and adventurous for me because I absolutely loved using the software before. I used to use it a lot in my classes for assignments where I would be designing simple shapes, but actually getting a chance to use it to design the structure, knowing that it would be built to serve a real-world application, was something totally new to me, and not to mention very, very exciting. So after the design was done, I started doing some structural analysis using SolidWorks simulation, because after all, I had to make sure that the design that I had done would survive the forces from launch. It would be able to support the entire weight of the satellite, including the forces from the rocket as it took off, as it experienced large amounts of acceleration. I basically used SolidWorks simulation. It's a side package of SolidWorks. And I was basically looking for stress concentrations on the structure after a load was applied to see where potential failure points could exist. These two frames, the left frame and the right frame, are the most critical structural components because they hold the entire weight of the structure, because every structural component, including the electronics inside, are fastened to these frames. To give you a better a view of the frame, I'm going to take apart this left panel so that you can see inside the satellite and see the design of the frame. And so the left panels came out, and this is the left frame. You got 2 posts, and what connects them are these crossbars, and it's basically one piece machined out of aluminum 7075, and the reason why it's black is because it's hard anodized so that the surface can withstand the harsh space environment. So getting back to the stress analysis, I mentioned that I was looking for stress concentration points on the structure after a load was applied to see where failure points would exist. The main purpose of doing this was to determine if the structural design was viable for spaceflight. The results from the test concluded that the structure could actually withstand launch forces. After the analysis, it was time to finally build the structure. Now that the design was finalized and we were confident in the structure being able to withstand all the launch forces, we were ready to manufacture all the components. And again, I was in uncharted territory. This is something I'd never done before. It was completely new, and I was again very excited to learn about this process of manufacturing. So I had to go out and find people who could make these parts for us, and I'd never been to a machine shop before. So in the period of a few months, I visited many machine shops, received many quotes. Sometimes I've even gotten comments back from some of the machinists saying that it would be almost impossible to manufacture some of the parts. The hardest part were the frames, because they had so many features on them, and it was so small that it would be very time consuming, and it would be hard and difficult to manufacture it. After months of relentless searching, I basically found someone who could make it for us. I learned a lot from this person, this machinist, and a couple of the manufacturing engineers at the machine shop about the idea of design for manufacturing and design for assembly. You know, it really opened my eyes to ask myself questions like, how can I reduce the time it takes a machinist to program the machine to make me this part? Or how can I design this so that there aren't any complicated setups required, so that all it takes is one simple setup on the CNC machine and you could start machining the part right away. The first time they went to manufacture the frame, they had to create numerous setups because there were features where you couldn't just machine out from one setup. You had to turn the part over and begin machining on the other side. So now I've come to the point of this presentation where now I want to present several pictures from slides on my computer that show detailed drawings that I created for some of these structural components, like the frames. In these slides, I've also included some more pictures from the project that I'd like you to see. Here's a drawing of the right frame. This is one of the many drawings that was given originally to our machinist to fabricate the structure. You've got the left view, the right view, the front view, top, bottom views, and finally the back view. And this drawing was created in SolidWorks. Here's a picture of me in the lab of our project lab, assembling the structure after I received it from the machine shop. I'm going to take this camera a little bit closer to give you a better view of some of the parts. Now, the project that I just showed you, everything had panels on it. This is now almost stripped. Only about 3 panels are connected to 2 of the frames. You got one of the frames at the top right here. It's one solid piece, like a square shaped. And I am assembling the electrical power system PCB. The PCB that's responsible for regulating and distributing the power from the batteries and the solar panels from the satellite. And you can see the front axis panel as well in this. And the main point of this assembly was just to see if everything from the machine shop came out perfectly, so that all the inside electronics could assemble properly into the structure. Here's another assembly view. Now the satellite is sitting upright, and you can see the front axis panel, the imager, the EPS, electrical power system PCB. An example of a secondary structure right here, this is the battery press, this metallic plate with screws at the end, and it's basically responsible for holding down the batteries to this larger plate that's attached to the structure. So both these structures, this battery press and this larger battery plate, are examples of secondary structures where they're not part of the main structure, but they're part of the structure subsystem in the sense that they hold down the equipment to the main structure. This is a very interesting picture because we got a chance to meet Jeff Ray, former CEO of SolidWorks, at SolidWorks World, where he was presenting where he wanted to introduce our project to 5,000 members of his audience at SolidWorks World 2010 in Anaheim, California. And he's holding a rapid prototype model of our satellite, UCISat-1, and it's almost an exact replica. It's just in a rapid prototype, so different material, and he's got the antenna sticking out, so you can see the front axis panel right there. And the reason why Mr. Ray is introducing our project is because he was looking for some project that was demonstrating excellent design skills and a challenging design using SolidWorks. And so I met Mr. Ray through my engineering mentor, who recommended that our project should be used in this SolidWorks World 2010 event as a showcase. And it was very nice because most of our team got a chance to meet Mr. Ray, and everyone had a chance to go down and see this SolidWorks World event and meet a lot of industry professionals. And here's a picture of the satellite, almost entirely assembled with solar panels on the outside. The satellite is just missing the front axis panel, but you can see all the electronics that pack into this little volume right here. It gets a bit dense because it's such a small cube. It's about 10 by 10 by 10 centimeters total size. These are the solar panels and the green PCB. They're assembled onto a PCB, and behind this green PCB is the one of the panels, the structure that I designed. You can see one of the posts for one of the frames, the imager, and that electrical power system PCB that was in the earlier assembly photos. Here's a picture of me and some of my team members and our project advisor, Professor Benjamin Viak, on my left, and with his colleague Martin Lowe of JPL on my right. This was taken on Senior Project Display Day at UC Irvine, a couple days actually before my graduation, and we're presenting our project almost finally assembled and ready for testing and launch. And this concludes my project presentation. I hope that you have enjoyed the project that I've shown you, and that I have the opportunity in the future to meet you in person. Thank you very much for your time. Have a great day.